Hello, everyone. My name is Yilong Li, a PhD student at the University of Wisconsin-Madison. Today, I will introduce our research work, which was also worked with Eugene, Professor Suman Banerjee. In this project, we explore the design of a platform to enable wideband mobile spectrum sensing on a heterogeneous computing processor. Monitoring spectrum usage has been a problem that the community has attempted to address over decades. With increasing demands of wireless capacity and 5G services, spectrum policies are becoming more flexible, and FCC has planned new frequency bands available for diverse use cases. So they include recent developments in low, mid, and high frequency bands. The spectrum sensing is becoming more important. Our question is, why do we need mobile spectrum sensing? The answer is because static spectrum sensors cannot achieve fine-grained coverage. The second question is, can existing platforms achieve mobility, low cost, and high performance at the same time? Answer is no. So the high performance and low cost mobile spectrum sensor is needed at this time. Typical spectrum sensing system deploy a set of static spectrum sensors, which are connected to a PC host and eventually to cloud-hosted servers for data analysis. Most low-cost spectrum sensing systems use resource-limited spectrum sensing hardware, like RTL. RTL is a USB dangle that has very limited frequency range and a very low sampling rate. Some platforms use high-end RF front-end, frequency translator, and high-end processor to build a relative uh, complex RF sensor like ThinkRF. It's stationary and a lack of mobility. Also, most practical deployments of these spectrum sensors when used for wideband sensing rely on desktop computer as a computing capability resource, which cannot achieve mobility. There are also other commercial spectrum sensing platforms like LimeSDR. LimeSDR is very popular, provides higher performance than RTL, and it uses an FPGA of Altera. Okay, the biggest advantage of LimeSDR is that they use their own transceiver and has a USB connection, but it's not easily for LimeSDR attached to a mobile device. It relies on computing capability of PC host. USRP is widely used and very famous. It usually needs a connection to a PC host via a USB or Ethernet. The E320 also has a standalone mode and it allows users to put all necessary computation on the platform, but it uses Ethernet interface. We know that mobile devices don't have an Ethernet port, and it's stationary and has a large size and needs an external power supply. So this limits its mobility. Traditional spectrum sensing devices are always using RF front end and needs a connection to a PC host via USB or Ethernet. The PC host provides the computing capability for various sample processing. Also, they always use a general purpose processor inside desktop computer. It's not optimized for real-time wireless signal processing and the lack of reconfigurability. Almost all prior spectrum sensing efforts rely on static sensor. Can we achieve a balance of low cost and high performance for mobile spectrum sensing? We don't want high cost front end, which is very bulky, and the low cost devices that has a very low performance. Our platform uses a highly integrated transceiver to provide wide bandwidth sensing with low cost and sufficient computing capability provided by a heterogeneous computing processor, Zinc 7020. So Zinc 7020 has both an ARM-based processor and an FPGA unit inside. This is a performance comparison with other commercial spectrum sensing platform. Mobile phones can connect to an RTL SDR dangle via an OTG interface, but it can only provide very limited frequency range. Lime SDR is very popular, but it does not provide any support for mobile phone connection and has a very limited mobility. Our platform can achieve wideband spectrum sensing and also has mobility, also an onboard computing capability. Now, let me introduce the system design. In order to build a mobile spectrum sensing platform, the first challenge we will meet is the data transference throughput. Traditional spectrum sensing hardware usually needs an RF front end connect to a PC host via USB or Ethernet. The high-end SDR platform will use Ethernet or provide sufficient data bandwidth to the host to be compatible with their high sampling rate front end. So they always rely on computing capability from PC host, and data transferring bandwidth limits the sampling rate. Smartphone can only use USB OTG, and this will make the front end cannot achieve its maximal sampling rate. And the existing mobile CPU is a general purpose processor, and it's not optimized for baseband processing. Heterogeneous computing processor provides a new opportunity that is a commercialized SoC and works for both for general purpose processing and also reconfigurability. In our system, processing system, which is a dual-core processor responsible for operation of system control and synchronization of each hardware module, the programmable logic, which is an FPGA unit, takes its advantage of reconfigurability, real-time and parallel processing in wireless communication to support high-speed wireless protocol. They are connected via an AXI interface, which has a very high bandwidth and throughput. So using a heterogeneous computing processor can provide both reconfigurability and sufficient onboard computing capability. For our solution, different from existing spectrum synthesis system, we put the wireless signal processing functions, including baseband processing on onboard processor, for which enables high processing speed, and also it does not rely on computing capability from host. The RF front end uses an advanced, highly integrated transceiver with a high sampling rate. It transfers digital and high fidelity wireless samples to the digital processing controller. So in our system, we remove all bottlenecks of the data path from the RF front end to the wireless signal processing module and have capability of connecting the mobile devices. This is the architecture of our system. The wireless signal will first enter the transformer and the mixer for RF pre-processing and the impedance matching. The transceiver transfer digital and high fidelity accurate samples to processor. The processor will divide the workload and transfer data via AXI interface. We make use of these features of the onboard computing processor, Zinc 7020. This enables our platform to sense and analyze a wide range spectrum with high sampling rate in real time. In spectrum sensing applications, the RF front-end performance is the most important because it needs a wideband sensing capability and high resolution of sample signal, but also result in a high data rate of IQ samples that need to be transferred to the digital processing unit. Our platform uses a customer designed front end that provides a wide frequency band sensing with high sampling rate based on AD9361 from analog device. The IF front end transfers a high volume of IQ samples data stream to the digital backend. Our digital processing backend places all necessary computation and modulation processes on the processor. In our software part, we spend our major effort in developing both the firmware for our hardware and the driver for Android phones. The firmware is loaded into the Zinc 7020 coprocessor via USB driver when the hardware is powered up. When the hardware device connected to a host, the driver will first verify the device and then load the pre-compiled firmware into the FPGA's memory field through the USB controller. The driver on Android phones supports developers to build their own apps that connect to our hardware device. Next, let me introduce our implementation details. This is our hardware implementation. It's the PCB design. We can see we conducted a very compact design with a small size. And this is a small, simple demo on Android phone, the Google Pixel 3a. We also modified an Android driver based on an open source framework. Integrates GNU Radio so that our platform can connect to Android phones via a USB OTG cable. Using the Android compatible GNU Radio framework, it's convenient for the community developer to develop Android apps that works on our hardware based on GNU Radio. So this figure shows the starting mobile app to provide basic control functions. It's display the spectrum option from our hardware device. So now we are using the driver, open source driver from this framework, and also the Plato SDR driver from ADI. In the future, we are going to develop our own driver on this hardware. Now, let me introduce the evaluation part. In evaluation part, we show the performance of our platform in spectrum sensing application. The Bluetooth signal hops randomly and very fast, which makes capturing a single pulse very difficult, and it needs high sampling rate of hardware. This figure shows how our hardware device capture single Bluetooth hopping. So this Bluetooth frequency signal hops to a different position. In this part, we show how our hardware senses a wideband frequency signal. Sensing 5 GHz Wi-Fi signals needs a hardware that has a wide bandwidth in both the front end and the digital backend. So our wide bandwidth hardware can capture the whole 5 GHz, 40 megahertz bandwidth Wi-Fi signal. So this is a small demo we prepare to show how our spectrum sensor capture the fastest signal like BLE hopping. Okay, we can see the signal hopped to a new position. And there is also the interference from 2.4 GHz Wi-Fi. The Bluetooth signal always hops very fast. In this part, we evaluate the power consumption of our hardware when it is powered by a Google Pixel 3a. If you are using Google Pixel 3a as only power source to power the hardware device, it can support 3 hours and 22 minutes of usage. If you are going to use a battery box with 4 18650 batteries, it can support 3 days of consistent spectrum sensing at power saving mode. The power saving mode is a mode that in our firmware, you can turn off the transmitter of the front end to save the power. So in spectrum sensing application, you are always using the receiver only mode. So this will save almost 50% power consumption. Finally, let me summarize our contribution in this part. We propose a new design for mobility, reconfigurability, and high performance wideband spectrum sensing. So our platform uses an appropriate core processor to achieve both of low cost and high performance. It has a wideband and high sampling rate as front end, and it does not depend on computing capability from PC host. And we also, in our hardware, we also provide full control of all processors and the memory file to users, and users can load their own firmware, implement any functions on the hardware. So it's different from the existing commercialized platform that they need to use the official software. We also put all wireless signal processing and computations on board. And we also demonstrate the feasibility to connect it to an Android-based mobile device. In our future work, we mainly focus on large-scale sensing by mobile users. With a mobile phone connection, we believe our platform can provide large-scale spectrum sensing by mobile users. We hope it can be an integral part of finding spectrum sensing applications. There are also some challenges, right? For example, the privacy of mobile users' trajectory or locations will be a problem because the metadata are collected by the platform and usually need to transfer along with spectrum reading to a centralized cloud and do further analysis. Yes, that's a problem. But we believe that there is still potential to deploy such applications using our hardware in the future. Thank you. Thanks for listening.